Okay, so this is Soumen from IIT Kanpur. So in the last, so I'm from IIT Kanpur, a PhD student. So I was actually giving a lecture on the plus 11 organic chemistry, some basic principles and techniques. So far, the last lecture we have discussed about the what we have discussed the resonance effect. The resonance effect, plus R effect. Resonance effect is the we can also designate it as the R effect or EM effect, and then the positive resonance effect, that is plus R effect, minus R effect. We have discussed in the, and then we have discussed about the electromagnetic effect, the plus E effect, minus E effect. This is negative effect. Then today we are here. We'll discuss about the stereochemistry. Okay. So in lecture 6, we will discuss about the stereochemistry. So in stereochemistry, so what is actually stereochemistry? So whenever you will go to a organic chemist, whenever you have to deal with the organic chemist, so you have to come across with the stereochemistry. You have to well, how can I say, means well knowledge of the stereochemistry. Then only you can understand the organic chemistry very well. So the stereochemistry is the branch of chemistry which deals with the three-dimensional structure of the molecules and their effect on the physical and chemical properties, known as the stereochemistry. So they are saying the branch of chemistry. So the branch of chemistry, there are different kinds of chemistry. So like inorganic chemistry, physical chemistry, and also the organic chemistry. So in the organic chemistry, one of the important stereochemistry. So I'm going to uh, explain the stereochemistry in this lecture. So the thing is that the which deals with the three-dimensional structure. So the three-dimensional structure of molecule and their effect on physical and chemical properties, known as the stereochemistry. So this is called the stereochemistry. Okay. So now we need at least one sp3. We need at least one carbon sp3 hybridized. Then we need at least one carbon sp3 hybridized, and also, so let's say we have an example of this one. Suppose I'm talking about CHI, then chlorine, and then bromine. So now how we can draw in a how to know what is the stereochemistry of the product. Now if we draw, you can see here I have drawn it is in the chem draw. So if you draw in this way, suppose C, hydrogen. Okay, now here it is iodine. Now here it is a bromine. Now here it is a chlorine. Okay, so this is called the sp3 hybridized and CHIClBr. Now 2D drawing not appropriate for the. This is actually 2D drawing. So actually it is not appropriate for the stereochemistry. Now we'll go to the 3D movie, 3D drawing. Now if you see the proper orientation of this 3D drawing appropriate for the stereochemistry. So if you see the structure, so here, so CH I Cl and Br. So if you see the structure, C, hydrogen, iodine, chlorine, and now it is bromine. So now if you want to draw in a 3D manner, then what we have to do? So either chlorine will be below, not a solid bond. This is called solid bond. So this is called actually solid bond. This is called solid bond. Okay. This is called dash bond. DASH, dash bond. Okay. And now another bond will be the above. So one is the below to the carbon, and another, this bromine, will be the above to the bromine, above to the plane. So this is, if this hydrogen and iodine if in a plane, then bromine will be above and chlorine will be below, right? So now if we write in this way, okay, this is the chlorine and bromine atom. Okay, so now in this way, so how the plane actually, the molecular plane. So if you see the molecular plane, if you want to see the molecular plane, I can also draw here. So let's say this is a molecular plane. Okay, so carbon is here. So one, and then here. So let's say here it is iodine is here. Now here hydrogen is here. Now above to this is, let's say this is the whole is a plane. So hydrogen and iodine in a plane. Okay. So now the chlorine will be below. So let's say this is a chlorine. Okay. Now bromine is the above. Above me. So this is the plane. So then above to the one bond will be there. Then there it will be bromine will connected to this. Bromine is connected to the carbon atom. Now isomers. So isomers is the constitutional isomer or structural isomer. So this is called constitutional isomer or structural isomer, and this is a stereoisomers. Okay, so isomers can be divided in a two way. So what are the isomers? So one is the constitutional isomer or structural isomer, and another one is the stereoisomer. Now, so what is the constitutional isomer or structural isomer? So isomers differ in connectivity of their atoms. Okay, so isomers differ in connectivity of their atoms. So we'll discuss all the examples also here. Okay, then only we can understand. So let's say first we'll go to the definition. So what they are saying. So constitutional isomer or structural isomers is the isomers differ in connectivity of their atoms. Now the stereoisomers is the isomers with difference in 3D arrangement only. So the stereoisomers is the isomers with a difference in 3D arrangement only. Now the stereoisomers is the two types. So one is the conformational isomer, and the second one is the configurational isomer. So the conformational isomers is what? So the conformational isomer is the isomers which are readily converted into each other through a single bond. Isomers which are readily converted into each other through a single bond. So if the isomers can be easily converted to each other through a single bond, then only it is called as a conformational isomer. And what is configurational isomer? So there will be no rotation possible through a single bond. So there is no such rotation is possible through a single bond. Then only it is called as a configurational isomer. Okay. Now we'll go to the second part. What is the second part? So in the second part they are saying about, so now the configurational isomers can also be divided. Configurational isomer can also be divided in a two way. So one is the geometrical or cis isomer, and another one is the optical activity. So the optical activity. So what is actually optical activity? We'll discuss this one also. I will discuss in the later slides. So what is optical activity? So we know that. So let's say first we'll go for the definition. What is optical activity called? So we know that ordinary lights are composed. We know that the ordinary lights are composed passing ordinary light by passing ordinary light. Now the bypassing ordinary light through the polarizing nickel prism. Such light whose vibration occur in only one plane is called the plane polarized light. So plane polarized light. Okay, we'll discuss this. How the means the we can also discuss the. We can also draw how it showing the plane polarized light. How the light is going through a molecule, and then only if one molecule is optically active, then it will show the rotation either plus or minus. We'll discuss it here. So now, so the rotation will be possible in a negative direction or clockwise direction, or else anti-clockwise direction. So if the compound, so upon passing the light through a compound, if the compound rotates the plane of polarization to the right clockwise, it is said to be dextrorotatory, plus or D. Now laboratory. So what is laboratory? If the compound rotates the plane of polarization to the left anti-clockwise, then it is said to be laboratory. That is negative or L. Okay. So dextrorotatory and laboratory. So if the compound rotates the plane of polarization to the left or anti-clockwise, then it is said to be the laboratory negative or L. Or if the compound rotates the plane of polarization to the right clockwise, it is said to be the dextrorotatory, plus or D. Okay. Now the optical rotation, the change in the angle of plane of polarization is known as the optical rotation. So what is optical rotation? The change in the angle of plane. The change in the angle of plane of polarization is known as the optical rotation. So this is called the optical rotation. And the polarimeter, how the polarimeter reacts, means how the polarimeter actually occur in a molecule. When we inject a sample in a polarimeter, then how it can be the instrument, how it called the polarimeter, it's called the optical rotation is detected and measured by an instrument which called the polarimeter. So this is the formula of the how to formula of the how to measure the specific rotation or observed rotation, observed angle of rotation. This is called the specific rotation. So alpha d is the specific rotation, specific rotation. So this is called the alpha is the specific rotation. Where alpha, lambda t, what is this alpha, and what is L, and what is C. So alpha is the specific rotation. As here I am right here already, it is also written here. Alpha is the specific rotation, and the T is the temperature of the T. This is called T. So T is the temperature. T is the temperature of measurement. So in which temperature you are measuring your sample? Let's say your temperature is when you are fixed temperature in polarimeter, it is 20 degree. Then you have to constrain this temperature 20 degree. Let's say so. Every high resolution instrument is always kept on the AC around with the AC room. So let's say when you are running a sample in a 20 degree Celsius, then you have to run all the sample in 20 degree Celsius only or 25 degree Celsius. In which temperature you will measure one compound, you have to measure all the compound the same temperature. So that means the temperature should be same. Okay, constant for the all the compound. Now we'll go to the lambda. So what is lambda? So lambda is the wavelength of the lighting. So in the polarimeter there will be one light. So plane polarized, right? When we switch on the polarimeter there and we inject the sample, then there will be a passing of the light through this compound. Okay, so the which always light has always all the lights always has some wavelength. So which wavelength already fixed in the polarimeter, we have to take this wavelength of this light. So that it is also done. So we are also done with the wavelength of the light used and the observed angle of rotation. Suppose here you are measuring, suppose polarimeter you are using, and there will be one screen. Okay, so let's say this is a screen, and upon start the when you start the measurement, then you will see some data will show 0.0818 80 or 81 or 0.172, like that it will show. So this is called the observed angle of rotation. So how it is showing? So if they will show the positive charge, then it is a positive value. So then it is a positive. If it is showing the positive, then it is positive means D, dextrorotatory, means the plane of polarization right to the clockwise. If the compound rotates the plane of polarization to the right side, so that means the compound rotates the clockwise direction. So that's why it is showing the plus. So it is a dextrorotatory. If it will show the negative region, so like if it is see the 0 point minus 0.08 or minus 0. Let's say 1, this is for an example just 172, then it is an anti-clockwise. Then the compound is rotating to the anti-clockwise. Okay, so let's say this is the screen. Now if it is showing the negative value, so this is the negative value, it is showing negative value is the same, but if it is show the positive value, then it is dextrorotatory. If it is the showing the negative value, then it is a L, laboratory. And if it is showing the positive value, then it is just showing the, then it will be the D, mean the clockwise. Because here I have already shown you that if it is showing the clockwise, then plus or D. If it is showing the anti-clockwise, then negative or L. So that means if somewhere it is showing negative value, then it is a L compound. L compound. If it is showing somewhere positive, then it is a dextrorotatory or positive. Clockwise. It is rotating in the clockwise direction, and it is a D. Now it is a plus or D. Now we'll go to the length L. So what is L? So L is the length of the sample tip in decimeter. So whatever length we are using in the polarimeter for a sample tube decimeter, so whatever it is, let's say X. So then we have to put the X value. What is X? X for the length of the decimeter. Then the concentration of the sample gram per solution. So whatever concentration you are using, let's say you have a 10 mg of compound. Let's say 10 mg of compound. But 10 mg of compound. Now how to determine the concentration of the sample? So now you have to 10 mg means you have to convert into the gram. So now if you convert into a gram, so that means milligram to gram means into 10 to the power minus 3. So okay, 10 into 10 to the power minus 3. 10 into 10 to the power minus 3. So that means what will be the value? So 0.01, because already one is there, 1, 2, 3. No, 1, 2, 3. So only 0.1. Sorry. So this will be the 0.1, not 0.1, 0.01. 0.01 gram. Okay, so 0.01 gram. Okay, now we'll go to the ml. Let's say then you use, so 10 mg with 5 ml solvent. With 5 ml solvent, you used let's say 5 ml solvent. Okay, now so 0.01 divided by 5. So if you divide it, then you will get the C value. So now you get the C value. L value you have from the instrument. Alpha value you will see in this screen. And you will get the this value from the screen. You have the L value from the instrument. You are using the compound and how much gram, how much mg. So from that you will get the one concentration value. Now you can easily get the specific rotation of this compound. So let's say alpha value is the X. Now we'll determine the alpha value. So let's say alpha value we want to determine. So we have observed the observed angle of rotation is the, let's say, X. Okay, and divided by L. L is the, let's say, 1. Okay, 1. Okay, 1 is the decimeter for the let's say 1 decimeter for the sample tube. Now you have a concentration. Let's say concentration is your Y. So what will be your alpha value? Alpha value will be X by Y. So X may be any number, Y may be any number. Okay. So in this way, you can also determine the specific rotation of the compound. Now we'll go to the next slide. So what is chirality? So now if we discuss about the chirality, so what is chirality? So what is chirality? Now we'll discuss about the chirality. Now if you see the chirality, so let's say chirality. We'll discuss about the chirality. Okay? Chirality. So now the chirality is an object which is not superimposable upon its mirror image is called the chirality. The term asymmetric center and the chiral center. Now we'll slowly going to the asymmetric version of this, means the little bit depth of the stereochemistry. Okay, now we'll use the term asymmetric center and the chiral center. So an object, what is called chirality. So an object which is non-superimposable, which is always remember, which is not superimposable. impossible, super impossible, which is not super impossible upon its, which is not super impossible uh, upon its mirror image. And its mirror image. Its mirror image. Then it is called the, then only it is called mirror image. Then it is called the chirality. Then it is called the chirality. Then it is called the chirality. So three terms are used to designate a carbon atom bonded tetrahedrally to four different substituents in a chiral molecule: asymmetry atom, chiral center, or stereo center. So three atoms are used to designate a carbon atom bonded tetrahedrally to four different substituents. So let's say this is a carbon center. So this is a carbon center. You can see this is a carbon. So A, B, C, and D. So three terms are used to designate a carbon atom bonded tetrahedrally to four different substituents in a chiral molecule. So asymmetric atom, chiral center, or stereo center. Okay. Now we'll go to the one by one example. Let's say this is the ABC. If we go to the true example, let's say true example is the C. So let's say here it is a CH3. So let's say here it is the iodine. Now here it is a chlorine. Now here it is bromine. Okay. So now this carbon has four different atoms. Then only this carbon can be called as a chiral center or stereo center. This is called chiral center. So this carbon you can also designate as a star. So that means this carbon is a chiral molecule, chiral center here. Now we will go to the, this is the central chirality. So you can see here. So let's say this is a carbon molecule. Okay. So one carbon molecule can, so let's say I'll draw this one first. So C. So then here one chlorine atom is here. One CH3 atom is here. One bromine atom is here. Below to this carbon is the bromine atom, and here it is a hydrogen molecule. Okay. Now, so this is there given in the star molecule. Let's say if I consider the only this molecule, so then you can see this is a chiral molecule. Why? The asymmetry has a four different atoms. So this is also different. This is also different. This is also different. This is also different. So four different atoms, four different molecule attached to a carbon center. So then only it can be called as a asymmetric or at four different molecule as a chiral center. Now I'll go to this second example. So how it is going? So let's say CH3 first. First it is a CH3. Then it is connected to a Br. Okay. Now here it is a one hydrogen here, one hydrogen here, and one hydrogen here. Okay. So now you can see if it is a carbon center. Okay. So now one carbon has CH3 and Br. Okay. Two different group is there. Now the third group is the hydrogen. Okay. And again fourth group also hydrogen. So that means we know that from the chiral center definition, this carbon has to attach to four different atoms. Then only it can be called as a chiral center. But here only three different atoms attached to a molecule. But in case of two other atoms are almost the two other atoms are same. So that means we cannot say it is a chiral molecule. So like here also we have written the chiral does not have a four different atoms bonded to the carbon. This is not a chiral molecule. So with this, because this is if it is not chiral, then we can also write it as this is a chiral molecule. If some molecule is not chiral, then you have to say this is a chiral molecule. This is a chiral molecule. Okay. Now this carbon has four different groups bound to the carbon. So one is so let's say we'll discuss about this one. So CH3. Now here it is a bromine. Now here it is a CH2. Okay. Now here is another CH2, CH3, and here it is a hydrogen. Right. So then here is a chiral, but has four different groups bound to the carbon. Okay. So CH3 Dr, hydrogen, and CH2, CH2, CH3. So chiral has four different groups bonded to the carbon atom. Okay. Now we'll go to the. So you can see there are four different groups. Uh, one is the one is the methyl, one is the methyl, one is the CH2, CH2, CH3, different from the CH3 group, and another atom is the bromine, and another one atom is the hydrogen. So that means four different groups. So that means this molecule is the chiral molecule because it has a four different group to the bonded to the carbon atom. So it is a four different group bonded to the carbon atom. That means it is a chiral molecule, right? Now we'll go to the next one. So that is the so far we have discussed only one carbon atom has a one chiral center. So if one molecule has a more than one chiral center, is it possible for a molecule having a more than one chiral center? Let's say we know that big molecule used in a drugs or natural products. So now here we have three. Actually, I borrow one of the two example where the carbon contains more than one example. Let's say we'll discuss about the first this one. Okay, how it is more than one chiral center it is showing. Now let's say we'll draw first this one. CHO. Then what it is written? CHO. Then the last one is the CH2OH. Right? We can also write here CH2 CH2OH. Okay. Now the second molecule, second here, what it is written? The right side OH, left side hydrogen. Now you can also write here OH here and OH in the right side and hydrogen is the left side. Now here OH is also here and the hydrogen is also present here in the left side. So now we have we can see two chiral center here. Where? So one is from here and another carbon chiral center is the this carbon. Which carbon? This carbon who is the one chiral center and this carbon is the chiral center. How? Now the question comes in mind that how these two carbon will be the chiral. So we will go forward from beginning. So let's say this carbon one is the CHO and the second one is the OH, third one is the hydrogen and the fourth one is the whole ring system, whole molecule. So that means this carbon is a chiral. Confirm. So one chiral center we identify already. And we'll go to the second one. So let's say this carbon attached with one OH group. Okay, the second one is the let's say hydrogen, and let's say third one is the CH2OH, and the fourth one is the this whole above molecule. So that means this is also chiral center. So that means this whole molecule has a two chiral center. One is from here, another one is from here. Okay, confirm. So here also it is written like the same way, chiral with two chiral center, chiral with three chiral center. But here they are showing three chiral center. Okay, let's see. Let's draw this molecule first. CHO and CH2OH. So here it is a OH and it is a hydrogen here, and then OH and another hydrogen is also present here, and then hydrogen is present here and OH. Okay. Now we will discuss about the how many chiral center is present. So let's say we'll first pick this carbon. Okay. So this carbon has one CHO group, one OH group, one hydrogen group, and one whole molecule. So that means this is a chiral. Now we'll go to the second one. Now second one is the connected with OH group 1, and the second one is the hydrogen molecule, and the third one is the this one, this above molecule, and the fourth one is the this molecule. So now this center also has the four different group. That means this is also chiral. Now we'll discuss about the third carbon center. So third carbon center one OH is here, and the second group is the let's say hydrogen, and the third group is the let's say CH2OH, and the fourth group is the this whole molecule. So that means this center is also chiral. So that means total three chiral center. Total three chiral center. So total three chiral center. Now you can also discuss about the total three chiral center. So you can also see one chiral center done, second chiral center also there, third chiral center also there. So the whole molecule contains total three chiral center. So here also it is chiral with three chiral center. So this is the whole molecule is also chiral. You can see this is a chiral molecule, and this is also chiral molecule because two chiral center is there. Okay, so now you can see. So this is here we have also discussed two chiral center belonging one molecule and three chiral center containing molecule. Also, we have discussed two different examples where one molecule contains two chiral center, but the another molecule contains three chiral center. Now we'll go to the next one. So what is next one? So the stereogenic center or stereo center. The term stereogenic center or stereo center. So what is actually stereo center or stereogenic center? So the definition says that if one carbon center is stereogenic center or not, or stereo center or not, how to confirm? So let's say one carbon molecule contain four different atoms or four different groups. If we interchange between two of them, and if we get any new stereoisomer, then only we can say this center is the stereogenic center or stereo center. So the term stereogenic center or stereo center is the, so let's say you have a one carbon center containing four different atoms or four different groups. So now if we change any of them, if we interchange any of the two groups in such a way that after interchanging, so you will get the one new stereoisomer. Whatever molecule you will get, it will also give you a one new stereoisomer. Then only we can say this carbon center is a stereogenic center or the stereo center. We can also say this is a stereogenic center or stereo center. Okay, now we'll give an example. Let's say here we have taken one example. We'll discuss by drawing. So first and second are the enantiomer, that is non-superimposable mirror images. Hence the stereoisomer is hence the stereo center is the chiral center. Now let's say we have a CH2OH, CH3OH, and here is the one hydrogen molecule is present here. Now if we interchange between these two groups, let's say OH and hydrogen. So in this molecule, OH is the right side, hydrogen is the left side. Now if we interchange between OH will go to the right side, left side, and hydrogen will go to the left side, right side. Then what will generate? So you will generate what will be the molecule? Let's say this one you will generate CO2H, CH3. Now what I will do? OH will go to the left side because initially OH was the right side. So now OH is the left side. Now hydrogen will go to the right side because initially it was the left side. Now you see, so these two isomer is the different. Why different? Why different? We'll go how the R and S nomenclature will come. How will confirm what molecule is R or S? So what is R? What is S? So this kind of thing will go. Maybe the later talk I will go. Later lecture, in the next lecture maybe I will discuss how to find a stereo center R or S, whether it is R or S or re-psi phase or homoleptic, heteroleptic phase. This kind of thing I can also discuss there in the next slide. So what we will see, so you can see this is the stereoisomer. If we consider the stereoisomer 1 and this is the stereoisomer 2, now you can generate two stereoisomer at a time. Means this is also different from that, right? So that's why we can say this carbon center is the stereogenic center or stereo center. Now we'll go to the another new example. So let's say it is giving the CO2. Now let's say we can discuss. Even we can also discuss the. Now we discuss about the y-axis barabar. So let's say we have this molecule CO2. Okay, CO2, and here it is a CH3. So now we already in the first example we discuss about the OH. There is a two axis. One is the x-axis and another one is the y-axis, right? So this is the x-axis and this is the y-axis. So now only we have changed the we have only changed the x-axis. But if we change the y-axis also, we can also generate one new molecule. How? So let's say if we draw another molecule, if we change in this orientation around, if we change around the y-axis, then what we will get? So let's say CO2H will go to the down, CH3 will go to the above. Now CH3 will go to the above side and CO2 will come to the below. Now what we will get? OH and hydrogen is the fixed now. Now I fixed the OH and hydrogen. Now what I have? I have the four different atoms. But in one case CH3 was the below, but in this case CH3 is the above. So now we have it. We have also generating one new stereoisomer. So what is this? So this is the new stereoisomer. So in this way, we can also say this carbon also stereogenic center or stereo center. Okay. Now we can also give another example, bringing chlorine bromine side. Okay. Not only this one, we can also bring some of the new example. Okay, so before going to that, so first I'll discuss about the stereogenic center. Stereogenic center will done. Now we'll talking about the geometrical isomerism. So geometrical isomerism is the one is the cis isomer, another one is the trans isomer. So geometrical isomer is the two types. Geometrical isomer in this geometrical isomer is the two types. So geometrical isomer is the two types. So one is the cis, another one is the trans. Okay. So what is cis and what is trans? So one is the cis molecule and another one is the trans. Okay. Cis and trans. Now we can see. So what is cis isomer and what is trans isomer? So cis isomer is the molecule geometrical isomers where the two CH3 group will be in the same position, will be in the same side, and in the trans isomer where the CH3 group will be the opposite side. That is called the trans isomer. Okay, so 3 and 4 are not enantiomers, they are diastereomers. Hence, in this case, stereo centers are not the chiral center. So, and also one important thing, it is the first and second are the enantiomer of each other, non-superimposable mirror image. Right. So now hence the stereo center is the chiral center. So if it is a non-superimposable, it is not possible for in this case because the stereoisomer 1 and stereoisomer 2, new stereoisomer 2, is both are enantiomer to each other. So hence the stereoisomer is the stereo center is the chiral center. Now if we discuss about the geometrical isomerism, so cis and trans isomerism. So geometrical isomerism. So in the both cases, if you see cis in the same side, so in cis isomer, same side to big group, big group in the same side. Now trans is the opposite side of the same group but opposite side, same group in opposite side, same group in opposite side, then it is called the trans isomer, opposite side. Okay, so we'll discuss about the one example here. We have I borrow one example, that is the CH3. Let's say this is a double bond. Let's say this is the double bond. Okay, so this is the double bond here, and one hydrogen is here. Okay, one hydrogen molecule is here, and one methyl group CH3 group is above, and another CH3 group is here. Now, if you see the whole molecule clearly, so you can see in this carbon attached two molecule. So one is the CH3 molecule, another one is the hydrogen molecule. This carbon also contains two molecules. One is the CH3, another one is the hydrogen. Now the two CH3 onto the above to the means the same side. See, the hydrogen is the same side, CH3 also the same side. So that means I also said that in the geometrical isomerism, two isomers possible, one is the cis isomer, one is the trans isomer. So if you see anywhere, any molecule in a double bond containing where the bigger group or the same type of molecule, same type of group in the same side, then only you can say the cis isomer. So you can see CH3 and CH3, both CH3 are in the same side. So that means you can also call it a cis isomer. So this is the cis isomer. Now if you exchange this CH3 with this hydrogen, so let's say CH3 will go to the below and hydrogen will go to the above. Let's say we fix this part. Now we fix this part and we'll rotate this bond. Although it is not possible, rotating of this bond is not possible because it is not a single bond. So around single bond, rotation is possible. But when it is a double bond, rotation is not possible. So now if you fix this molecule and if you just exchange the interchange this molecule to CH3 to hydrogen. So let's say CH3 will go down and hydrogen will go above. Now we will generate another molecule where the CH3 and CH3 in the opposite to each other. Now it is a trans isomerism. Why? Because I said that I already told you that in the trans isomer, the same group in the opposite isomer. So now the CH3 group and the CH3 group are in the opposite isomer. Even you can also see here the hydrogen and this hydrogen also in an opposite isomer. Now you can also call it a trans isomer. Okay. Now this is also you can say the trans isomer. Okay. Now if you see anywhere, now the point to be noted that the 3 and 4. So let's say I recognized I already pointing that this molecule is the 3. I already, let's say I am considering this is the 3, structure 3, and this is the structure 4. Which one is the structure 4? Let's say this one is the structure 4 and this one is the structure 3. Now they are saying that structure 3 and structure 4 are not enantiomer. Why? They are diastereomers. Hence, in this case, stereo centers are not chiral centers. Why? In the previous slide, what we have seen, although you are interchanging two groups, but still you are generating a new stereo center, then it is a chiral center. But here, because there was one condition that the new stereo centers should be enantiomer to each other. But here, cis and trans isomer are not enantiomer to each other. So that's why 3 and 4 are not enantiomer. They are diastereomer. And hence, in this case, stereo centers are not chiral center. Now you can confirm that the stereo centers are not chiral center. So what is RI enantiomer? So if you have a R, now if you are any mirror image is here, and if you are generating an S center, or let's say you have a S and you are generating in a superimposable mirror image, there will be R isomer. Then these two is called as a enantiomer. These two are enantiomer to each other. You can say this is the enantiomer. And what is diastereomer? This is called the stereoisomer. And I will go to the geometrical isomer also. Geometrical isomer also I will go. This is called enantiomer. So let's say you have a R. Okay. But still you are generating R. Then it is not enantiomer. Not enantiomer. This is not enantiomer. Not enantiomer. Okay. Now let's say G isomer. In case of the geometrical isomer, let's say you have a Z, E and Z. What is E and Z? Z is the, let's say Z is the same side, same type of molecule. If the two bigger group in the same side, then it is called as the G isomer. If the bigger group in the opposite direction, then it is called the E isomer. Okay, opposite. This is the opposite isomer. This is the same side. Now, if you have a G isomer and you are upon mirror images, you are getting the G. You are also getting the G isomer. Then it is a enantiomer, or E to E, or E. You have a E isomer. You are also after mirror image. You are also getting E isomer. Then these are enantiomer. These are enantiomer. But let's say, suppose you have a G and you are generating another E center. Then it is not. Then it is not the enantiomer. This is called the diastereomer. That is, then the diastereomer will come to the picture. Diastereomer come to the picture. Okay. Then the diastereomers come to the picture. Okay. So now we don't have much time, but still I will go. Before I go to the question answer section, I will discuss another example. What is G and E? Then maybe the next class we'll discuss the question answer. So what is G and E? Let's say not only the same molecule. Let's say CH3, one double bond, and here one ethyl group, CH2, CH3, and one hydrogen. So this carbon bigger group is this one. and this carbon bigger group is this one. So you can see that two bigger group in the same side, then it is a G isomer. And just opposite to this isomer is the E isomer. What is opposite E? So let's say CH3, and there is a hydrogen here, and there is a hydrogen. This hydrogen is the opposite, and now you have a CH2 and CH3. Okay, so here you can see one. So this carbon bigger group is this one. This carbon bigger group is this one. So now it is opposite to each other. Now it is a E. So this is called G. This is called E. So what is the difference between G and C? So in the case of cis isomer, there will be both group will be same. So CH3, so then it will be also CH3. Then only it is called the cis isomer. But CH3, but here it is another than CH3, but bigger group compared to the third group. So then it is a G isomer. Okay. So maybe we can discuss a little bit more in that next class. Okay. Thank you. So whatever we have discussed today, so we have discussed about the chirality, optical rotation, and configurational isomer. Stereochemistry, we start from the stereochemistry, but stereochemistry 2D drawing is not appropriate for the stereochemistry. We have to always go to the 3D drawing. Then we have discussed about the isomers. What are the isomers is there? Constitutional isomer, stereoisomer, conformational isomer, and configurational isomer. And then we have discussed about the along means the within the configuration isomer, two isomer is possible, geometrical or system isomer, and the optical activity. Optical activity is the measured by the polarimeter, where the you can see, if you see in the polarimeter is the positive rotation, so that means the clockwise rotation, that is the D. If you see the negative rotation, that is the L, laboratory rotation. And from the observed angle of rotation, you can also find the value of the specific rotation. And then we have discussed about the chirality, how the chirality can be induced, and the chirality is coming to the one carbon center. Then we have discussed about the what is the chirality, how the molecule acts as a chiral or not, when the molecule contains four molecule different atoms, or the two different atoms, three different atoms, or then it is not chiral. A chiral molecule is the second example. Then we have discussed about the more than one chiral center containing compound. We have discussed two chiral center containing compound, three chiral center containing compound. Then we have discussed about the stereo center or stereogenic center, how the one when you are interchanging the between two groups, how we can generate another new stereoisomer. This is if there is an enantiomer, then only it can call it a stereo center. If this is the not after interchanging two groups, if they are not stereoisomer or if they are not superimposable to each other or not enantiomer, then you cannot say it is a chiral center. You can also say this is the diastereomer of this molecule. Then maybe the next class we'll discuss about the question answer. Okay, thank you. So I'm stopping this one today here. Maybe the next class we'll discuss about the question answer section briefly.